Welcome to Astronova, the channel where we simplify the complex world of machine learning. Here at Astronova, we believe that knowledge is power and that everyone should have access to the exciting advancements in technology. Our mission is to make the intricate and often intimidating field of machine learning accessible to all. To do just that, today we're going to delve into 4 pivotal machine learning algorithms. We'll be breaking down these algorithms not just in theory but also in practice by linking them to real-world case studies. Our aim is to demystify these complex concepts and show you how they're being used in various industries to solve problems, make predictions, and drive innovation. Whether you're a curious mind, a budding data scientist, or a seasoned professional looking for a refresher, you're in the right place. So, without further ado, let's dive into the fascinating world of machine learning algorithms. Starting off with one of the most basic yet powerful algorithms, linear regression. Imagine you're trying to predict the price of a house based on its size. The house size is your input or independent variable, and the house price is what you're trying to predict, your dependent variable. Now, imagine plotting these data points on a graph, with house size on the x-axis and house price on the y-axis. You'll probably notice a pattern. As the size of the house increases, so does its price. This is where linear regression comes in. It's a statistical method that helps us understand the relationship between 2 continuous variables, in our case, house size and price. By fitting a straight line through our data points on the graph, linear regression gives us a formula that can help predict the price of a house based on its size. This straight line is known as the regression line, and it represents the best fit through our data points. But it's not just about house prices. Linear regression is a versatile algorithm used in various fields like economics, finance, biology, and more. From predicting stock prices to forecasting crop yields, linear regression simplifies complex relationships into a straight line, making predictions easier and more accurate. However, it's important to note that linear regression works best when there's a linear relationship between the independent and dependent variables. If the relationship is more complex, other algorithms might be a better fit. And how do we know if our linear regression model is good? We use measures like the R-squared value, which tells us how well our regression line fits the data. A higher R-squared value means a better fit and a more reliable model. In essence, linear regression is like trying to draw a straight line through a scatter plot of data points. It's a simple, yet powerful tool that transforms raw data into meaningful insights, helping us make informed decisions in a world that's increasingly driven by data. Next up, we have logistic regression, not to be confused with its linear counterpart. Now, what exactly is logistic regression? Well, imagine you're a digital mail carrier and your job is to sort emails into 2 categories, spam and not spam. How do you do this? You use logistic regression. Logistic regression, in essence, is a statistical method used for binary classification. It's like a gatekeeper deciding which category a particular piece of data falls into. So in our email example, logistic regression would look at features of an email such as the sender, the subject line, and the content, and use these to decide whether the email is spam or not. The real magic of logistic regression lies in its use of the logistic function. This function takes any input and transforms it into a value between 0 and 1. In our case, it's telling us the probability that a given email is spam. If the result is closer to 1, it's probably spam, and if it's closer to 0, it's probably not. But logistic regression isn't just for sorting emails. It's used in a wide array of applications, from medical diagnostics to credit scoring. For instance, doctors might use logistic regression to predict whether a patient is at risk of a certain disease based on their medical history. Similarly, credit card companies might use it to predict the likelihood of a customer defaulting on their payments. What sets logistic regression apart is its simplicity and efficiency. It's relatively easy to implement and understand, making it a popular choice for binary classification problems. But like any algorithm, it's not without its limitations. It assumes a linear relationship between the independent variables and the logits of the dependent variable, which isn't always the case. So, unlike linear regression, logistic regression is all about classification rather than prediction. It's like a digital gatekeeper sorting through the chaos of data to help us make sense of the world. And in a world that's becoming more and more data-driven, tools like logistic regression are becoming invaluable. Moving on to decision trees, a machine learning algorithm that you can actually visualize. Imagine you're deciding what to wear today. You look outside. If it's sunny, you might pick your favorite t-shirt. If it's raining, you'd probably go for that warm, waterproof jacket. This is essentially a decision tree in action. Now let's translate this to machine learning. In the context of machine learning, a decision tree is a type of predictive modeling approach. It's called a decision tree because it starts with a single box or root, which then branches off into a number of solutions, just like branches and leaves of a tree. The best part about decision trees? They're incredibly intuitive and easy to construct. Each internal node of the tree corresponds to an attribute. Each leaf node corresponds to a class label, and the branches represent conjunctions of features that lead to those class labels. But where would you use decision trees? They're particularly useful for classification and regression tasks. For example, in healthcare, decision trees are often used to predict whether a patient will respond positively to a particular treatment. In finance, they can be used to predict whether a customer will default on a loan. The advantages of decision trees are many. They're easy to understand and interpret, even for people with little statistical knowledge. They can handle both numerical and categorical data, making them very versatile. Plus, they require relatively little data preparation compared to other machine learning algorithms. However, like all algorithms, decision trees have their limitations. They can be extremely sensitive to small perturbations in the data, leading to different trees being generated. They can also easily overfit the data, leading to complex trees that do not generalize well from the training data. So, a decision tree is basically a flowchart for making decisions. That's machine learning for you. Now let's explore the random forest, a group of decision trees working together. Picture this: you're part of a jury trying to make a decision. Each member has their own perspective, their own way of looking at the evidence. Some may focus on the motive, others on the alibi, and few on the physical evidence. Each of you votes, and the majority verdict is reached. This is essentially how a random forest works in machine learning. The random forest algorithm is a type of ensemble learning method where multiple learning models combine to solve a problem. In this case, the models are decision trees. Each decision tree is built on a different subset of the data and makes its own individual prediction. The random forest then takes a vote, and the most popular prediction becomes the final result. Let's consider a real-world example. Suppose Netflix wants to recommend movies to its viewers. The random forest algorithm might use one tree to consider a viewer's genre preferences, another to consider their past viewing habits, and yet another to consider the popularity of different movies. Each of these trees makes its own recommendation, and the movie that gets the most votes is recommended to the viewer. The beauty of random forest lies in its strength in numbers. By using multiple decision trees, it reduces the risk of overfitting, a common pitfall in machine learning where a model performs well on training data but poorly on new, unseen data. This makes random forest a versatile and robust algorithm, commonly used for both regression and classification tasks. It's also worth mentioning that random forest is great at handling large data sets with many input variables. It can easily handle missing data and maintain accuracy, even when a large proportion of the data are missing. So a random forest is just a team of decision trees, each casting a vote to make a decision. It's a democratic algorithm, if you will. Each tree gets a say, and the majority rules. This collective decision-making process helps to make the random forest one of the most reliable and robust machine learning algorithms out there. Now that we've covered these 4 key machine learning algorithms, let's do a quick recap. We started with linear regression, a fundamental algorithm that's all about predicting a continuous outcome. It's like trying to predict the price of a house based on its size. Remember, it's simple yet powerful, and it's the cornerstone of many complex algorithms. Next, we dove into logistic regression, which, contrary to its name, is used for classification problems, not regression. Think of it as a way to predict whether an email is spam or not. It's a handy tool when dealing with binary outcomes. Then we entered the realm of decision trees. They are intuitive, easy to visualize, and perfect for making decisions. Just like a game of 20 questions, decision trees ask a series of yes or no questions to arrive at a conclusion. Want to decide whether to play tennis or not? A decision tree could help you out. Finally, we ventured into the random forest, a collection of decision trees. It's like consulting a group of experts instead of just one. The random forest takes the majority vote from its trees to make the final decision. It's a robust algorithm that helps prevent overfitting. Understanding these algorithms is a stepping stone in the vast world of machine learning. They provide a solid foundation, a starting point, from where you can dive deeper into more complex concepts. Each algorithm we discussed has its unique strengths and applications, and knowing when to use which is a critical skill in machine learning. Remember, these are just 4 of the many machine learning algorithms out there. There's a whole universe waiting to be explored, from support vector machines to k-nearest neighbors and beyond. So don't stop here. Keep learning, keep exploring, and keep innovating. And that's a wrap. You've now got a basic understanding of 4 crucial machine learning algorithms. Thanks for tuning in to Astronova. Before we say goodbye, here's a quick reminder from Astronova. We hope you've enjoyed this journey through the top machine learning algorithms. If you've found value in this video, we urge you to tap that like button and share it with your friends, classmates, or anyone who might be interested in machine learning. Are you eager for more? Then don't forget to hit the subscribe button and become part of the Astronova community. We have a plethora of content in store for you, all designed to make complex concepts accessible and intriguing. And to ensure you never miss out, make sure to switch on notifications. That way, every time we upload a new video, you'll be the first to know. Remember, the world of machine learning is at your fingertips, and Astronova is here to guide you. Until next time.